This video covers thermodynamics, temperature, and ideal gas law. Temperature, represented by a capital T, is the measure of the average internal energy. Another way to say the average kinetic energy of an object or a system. The internal energy, represented by a capital U, is the energy associated with motion, again referring back to kinetic energy, of atoms or molecules. In a gas, this can be due to translational kinetic energy. Again, these molecules are moving, so they have kinetic energy. In other substances, molecules can rotate or vibrate, but we're not going to deal with situations like those. We're going to deal only with translational energy, meaning they're only moving in the linear directions. Now, before we can really talk about temperature, we need to talk about the three different type of temperatures scales that we've seen before. Now, you've seen the Celsius scale, the Fahrenheit scale, and now the Kelvin scale. On the Celsius scale, 0 is the temperature at which water freezes, and 100 is the temperature at which water boils. So if you memorize these two pieces, you can derive the other boiling points and freezing points of water in the other scales. The Kelvin scale is the SI scale for temperature. If a problem asks you to use temperature, you're going to be using the Kelvin scale. This is based on absolute zero. Absolute zero is the theoretical lowest temperature that an object can reach. Now, the three equations you're going to want to know are these three here. These are the conversions between our different temperature scales. This first one converts Fahrenheit to Celsius. The second one converts Celsius to Fahrenheit. And the last one converts Celsius to Kelvin. Again, all you really need to know is the boiling points and freezing points of water, and then we can use that information to solve for the boiling points and freezing points in the other two temperature scales. So again, right here in the middle, we have the Celsius scale. Over here, we have the Kelvin scale. And here we have the Fahrenheit. Now for problems, anytime that you see a T, again, we are using the Kelvin scale. So you need to convert all of the information into Kelvin. Now, if the equation asks for delta T, which is a change in temperature, you can actually get away with using Celsius or Kelvin, because a change in temperature for Celsius is the same as a change in temperature for Kelvin. That's not going to be true for a change in temperature of Fahrenheit. So if it's asking for change in temperature, use either Celsius or Kelvin. This section is on linear expansion. Again, you know that most materials expand when heated. So as long as the temperature change isn't too large, each dimension of an object experiences a change in length that is proportional to the change in temperature. Now, delta, again, is final minus initial, so L is going to be the change in the length of this object, where L naught is the original length of the object. So it's not an error to have L naught here and have L naught in here. That's okay. This alpha is the coefficient of linear expansion. This is going to be dependent on material, and also this number is very tiny, usually times 10 to the negative 6th power. Again, here you do see that change in temperature, so again, you can get away with using either Celsius or Kelvin. So remember that delta L is final minus initial. So if I move this initial to the other side by adding, then I get this equation down here. If I have an initial length here and here, then I can actually factor it out and end up with this version of the equation over here. So this is another very common use of that equation. You don't have to rederive it every time. You can either memorize both of them or memorize one and derive the second. The previous equation dealt with only the linear expansion, but we can also make this equation apply to an area expansion and a volume expansion. Just by changing the factor that alpha is being multiplied by. In this case 2, in this case 3. An ideal gas has to satisfy these conditions. It has to consist of a large number of identical molecules. The volume occupied by the molecules themselves is negligible compared to the volume of the container they're in. So again, the volume of the molecules is much, much smaller than the volume of the container. The molecules obey Newton's laws of motion, and they move in random motion. And this is specifically called Brownian motion. You don't need to know that, but it's a fun fact. The molecules experience forces only during collisions. Now, collisions are completely elastic collisions, meaning that there is no loss of kinetic energy, and that's going to be important later. And these take a negligible amount of time. Before we go into the ideal gas law a little bit more, we need to remember a few things from chemistry. Now, a mole is very similar to a dozen in the sense that it stands for a certain amount of things. So 1 mole is equal to 6.02 times 10 to the 23 atoms or molecules, or basically anything, but we use it for atoms or molecules. This is also known as Avogadro's number, and this could be represented as a capital N with a subscript A. Now we have two equations for the ideal gas law. The first one is the one you're probably most familiar with. It's PV equals nRT. P is pressure in pascals. V is volume in meters cubed. Lowercase n is the number of moles. R is the universal gas constant, and it is 8.31 joules over moles Kelvin. Here we have again that capital T, so we're going to be using absolute temperature or our temperature in Kelvin. Our second ideal gas law is very similar, but what we're doing is we are dividing our first ideal gas law by Avogadro's number, which is N. Multiplying by Avogadro's number. Again, this is simply the value 1. So what we're really doing is just multiplying this by 1 because anything over itself is 1. So, if that's true, then R over NA gives us a new constant, which is KB. This is known as Boltzmann's constant, and this is 1.38 times 10 to the negative 23 joules per degree Kelvin. Now, these constants you will not need to memorize. You will be given these values every time. This capital N now represents the number of moles times our Avogadro's number, which is simply the number of molecules. Again, if you go back and look at the conversion between molecules and moles. And everything else is the same. And the last piece before we put it all together is the kinetic theory. Now, this kinetic theory is the application of Newton's laws to ideal gases. What you do is you start with one atom of ideal gas in a box and determine the pressure associated with that atom. Then you add more atoms and average over all the atoms to see what you get. So again, what you're trying to do is solve for the average pressure due to the atoms. So a few results from the kinetic theory. Remember that pressure is equal to force over area. So pressure is associated with collisions of gas particles with the walls. So you have these particles floating around and they're colliding with the walls. And what happens is that they're applying a force over some area, creating pressure. Now, if you increase the temperature, then what you're doing is you're making these molecules move faster and faster. So the pressure is going to increase. 1, because there are more collisions with the wall, and because the collisions involve a larger average force. Think about impulse. If you're making these atoms move faster and faster, you're making the change in velocity get bigger. And so the force that they apply also increases. Now, the ideal gas law is true even though you may change different components of the equation. And we'll look at that in just a bit. The first example says a gas occupying a volume of 4 liters has a pressure of 6 atoms and a temperature of 25 degrees Celsius. The gas is heated, the volume increases to 12 liters, and the pressure increases to 18 atmospheres. What is a new temperature of the gas? Well, if the ideal gas law is all of this information at the beginning before you've increased the heat, and this is the ideal gas law after you've increased the temperature, well, then if we solve for R in both situations, then I know that this information must be equal to this information. If that's true, our equation now looks like this. So P naught is our pressure at the beginning, V naught is our volume at the beginning, N naught is the number of molecules we began with, and T naught is the temperature that we began with. Over here we have our final pressure, our final velocity, and our N, which is the number of molecules we ended up with. Now, our number of molecules did not change. The number that we had at the beginning, which is the amount of dots that we have here, is the same as the amount of dots or the amount of molecules that we have at the end. So these values are also constant. So what we're trying to do is solve for T, temperature, at the end. So rearranging this equation, I want to get T by itself. So not only do I want to get it by itself, I want to put it on top of my fraction. So my equation now looks like this. T times P naught V naught over T naught equals PV. And again, I want to get this T by itself, so I can bring this down to the bottom and T naught up to the top. So my equation now looks like PV T naught over P naught V naught. Now before I can plug in any of my numbers, I have to make sure all of my values are in things that I can use. Now 4 liters needs to be converted to meters cubed. So 4 liters divided by 1,000 liters gives me 1 meters cubed. So that moves my decimal over 4 places. So that's 0.0004 meters cubed for my volume. Not. The pressure is 6 atmospheres. So pressure is 6 atmospheres. But 1 atmosphere is 1 times 10 to the 5th pascals. So 6 times 10 to the 5th pascals is my pressure. The temperature is 25 degrees Celsius. So if I wanted to convert that to Kelvin, I simply add 273. So that gives me 298 degrees Kelvin. And my volume, again, I simply move my decimal over 4 spaces. So that's V is equal to meters cubed. And the pressure is simply 18 times 10 to the 5th pascals. So I can plug all of my information. Actually, it's only 1 decimal place. It's only 3 decimal places. So if I plug in all of my values, I should get a temperature of 2,682 degrees Kelvin. Another little trick you can see here is that my equation was T equals P V times T naught over P naught V naught. Well, the numbers actually worked out to where they were multiples of each other. The pressure increased from 6 to 18. That means my final pressure was 3 times my original pressure. My volume increased from 4 to 12. So, my final volume was also 3 times my original. And then my initial temperature stays the same. So if you notice here that these P naughts will cancel out and these V naughts will cancel out, and I'm left with 9 T naught, or 9 times our original temperature in Kelvin, which was 298. So 9 times 290 also gives you 2,682 degrees Kelvin. So again, this is very likely the way that you will see problems on the multiple choice section.